there are a few other magnetic effects that you should be aware of. What is termed paramagnetism is where unpaired electrons in orbitals make each atom a magnet, just like in ferromagnetism. But the difference here with paramagnetism is that paramagnetic materials do not form domains. So it's a weaker effect. When you place an external magnetic field, when you place a paramagnetic material in an external magnetic field, all the atomic magnets of the paramagnetic materials, they do align with the external field, and they do make the field stronger, but not by much. It's just a very small effect. It is much weaker, much weaker than ferromagnetism, like thousands of times weaker. But anything with unpaired electrons can be paramagnetic, so it's a lot more materials that are paramagnetic. And also, there's another effect called diamagnetism. Diamagnetism is something that all materials exhibit this. It causes, in contrast to paramagnetism and ferromagnetism, it causes a weakening of the external magnetic field, where in ferromagnetism and paramagnetism, the magnetic dipoles align, so they make the field stronger. In diamagnetism, you get a oppositely aligned magnet, which weakens it. They weaken the external field. The diamagnetism is a weaker effect than paramagnetism, and therefore is much weaker than ferromagnetism. I'm just going to give you a kind of a brief overview of how this effect is created. First of all, the thing to note that it's caused by electron orbits rather than electron spin. So it's a completely different effect than paramagnetism. Here's just kind of an overview, which it's not quantum mechanical, so it has a lot to be desired, but it'll just kind of give you a kind of a little justification for diamagnetism. So what we have here is an electron orbiting a nucleus. And again, they don't really orbit, but we can just kind of pretend that they do because it's very much like an orbit. And let's just say in this situation, the electron is orbiting counterclockwise. So if the electron is orbiting counterclockwise, what direction is the magnetic field caused by this electron just due to its orbit? Not due to its spin, which I've not included in here, but due to its orbit. So we have to use the left-hand rule for a coil, and the electron spinning around this way, so it's going to create a magnetic field that is into the page, like that, into the page. So the magnetic field, which I'm not going to show right here, is into the page. Now, what would happen if we created an external field? Let's go ahead and do that. An external field, we put this atom in an external field that points out of the page. So this is B external, out of the page, all around like this. Very strong magnetic external field pointed out of the page like that. Well, which way will the force on this electron be? Well, let's just look at it where it's right here. When the electron is right up here, now we've got to use our force on a moving charge. So we've got V going this way. We've got B, so I'm again using the left-hand rule. V going this way. B is going out of the page. So the force will be down on this thing right here. The force is down that way on this electron, F. Of course, when the electron moves over here, the force will be that way, and the force will be that way when it's over here. This will apply an additional centripetal force on the electron. This is force magnetic, by the way. There already is an electric force, and that is what is keeping the electron in its so-called orbit. But now we're adding another force. So what this means is that the electron is got to increase its speed. It must increase speed to in order so it doesn't fall into the nucleus. Got to increase its speed so it speeds up. Velocity increases. And what that'll do is that'll make it just more extreme. It'll be an even more extreme magnetic field which points the opposite way. So this is now a stronger field that the electron was creating before. This is the B field due to the orbiting electron right there. So that will have a tendency to weaken the external magnetic field. When you apply this external magnetic field that's out of the page, the electron speeds up, causing a stronger field into the page, and that weakens the external field. So that's just kind of a brief overview, and you might say, well, where does the energy come from to speed the electron up? That stuff's all in quantum mechanics, so we're going to skip all that stuff. But main idea here is diamagnetism causes a weakening of the external magnetic field. One way you can remember that is diamagnetism is kind of just like a dielectric. Dielectric does what to the external field when it's in a capacitor? A dielectric weakens the external field, and that's how you can have more charge on your capacitor, because it weakens the field. Diamagnetism, a diamagnetic material, which is all materials, will also weaken the magnetic field. Although everything is diamagnetic, it can be diamagnetic and paramagnetism is stronger than diamagnetism, and it can be diamagnetic and ferromagnetic, which is incredibly much stronger. So the ferromagnetic and paramagnetic properties, they tend to dominate, but when materials do not have unpaired electrons, then you cannot have ferromagnetism nor paramagnetism, so the magnetic properties will dominate.